of LCD codes, which will be presented by Dr. Buket Ozkaya. For Dr. Buket Ozkaya, time is yours.
Thank you. Okay. Well, the majority is back, I guess. I check. I think my father has 2 more hours in Turkey for the Friday prayer. I mean, he will be there in 2 hours or so. But it is, I mean, my father is retired as a security guard, and he was working in shifts. So in 2 of the 3 shifts, it is each of them for 8 hours. So he couldn't attend the Friday prayer for 2 of the shifts, because for the night shift he had to sleep, and the morning shift he was always missing. Now as a retired guy, now he's enjoying to be there with his friends every week. It is also a way of socializing, you know that, right? So I was checking, I mean, I always look at the time difference, and yeah, I think it is 4 hours between Turkey and here. So yeah, and I know more or less how long it takes. I mean, you have to attend the, you know, after speech, so to say. So this session will be a bit more algebraic. How many mathematicians are there here, actually? I am wondering. Can you raise your hand if you are a math student? Okay, majority. So, I'm not sure if everybody is into algebraic coding, of course, but as I said in the first hour, I mean, once this concept is introduced, many people attempted to generalize and provide explicit constructions for LCD, LCP type of codes from the code class that they know best of, okay? So this cyclic class is exhausted already, I mean, by the Massey himself. You know, I already told that, I mean, cyclic code is LCD if and only if it is reversible, if and only if the generating polynomial is self-reciprocal. So that case is done. LCP follows super easily. That I mean, we just taken care of that in a few lines of a proof in that big linear complementary pair of codes paper. I mean, it takes very, very little time to extend it to very little space even to extend it to the LCP case. So cyclic, I mean, in terms of the algebraic codes, that is also done. Many constructions, as I said, I mean, from algebraic geometry, non-algebraic geometry even, I mean, lattices and so on and so forth. I mean, many constructions are possible. And okay, I mean, the majority of my research is about quasi-cyclic codes, as I again mentioned. And I mean, today I will go over some works for you that are related to quasi-cyclic and its generalizations, okay? Let me recap for the newcomers, if there are any, I mean, who couldn't make it for the morning session, about the history of those people. Up. The definition, alternative definition is this. I mean, either you say C intersection C dual is trivial, or their direct sum add up to the full space. I mean, there are 2 equivalent characterizations of those. So, as I said, I mean, Massey studied them first for 2-user binary adder channel, okay? To send the data in terms of sums, like x plus y, x coming from one user, y coming from another, sending it in a decodable way. In that paper, he proposes a construction from an arbitrary linear code. I mean, given a linear code with a standard generator matrix, I mean, identity and let's say a redundant part P, you can construct an LCD. I will come to that, but he proposes that. He also proposes a minimum distance bound in terms of that arbitrary linear code. That gives us a statement, a strong statement, that can say, I mean, the LCD codes are as good as linear codes, arbitrary linear codes. Because, I mean, given a code, you can construct an LCD, so with a distance at least as big as that code given. So, I will come to that construction, but this is the first asymptotic result, so to say. I mean, about its distance performance, this is the first result that you can get. So, again, as I said, Massey Young in 94, 2 years after that, they studied the cyclic case, exhausted everything about it. Sandriem, 10 years after that, I think the most remarkable result is, I mean, okay, he does some explicit enumeration in terms of the LCD codes, etc. But one remarkable thing is, which I will verify you with the examples later, that he showed if you, I mean, the density, so-called the density of LCD codes among all the linear codes of that length and dimension is more or less this, okay? I mean, for binary, it corresponds to half of the codes that you are considering among the linear codes can be LCD. But once you raise the field size, over Q equals 3, for instance, it is 2 over 3. It becomes 3 over 4, and goes up. I mean, the density becomes higher and higher. And let me recall, I mean, I'm not sure if anybody is interested in the self-dual codes, but they are very rare. That is also a known result. And this is consistent with that. Okay? Self-dual codes are good for certain purposes, but they are very rare. So, again, that rediscovery paper in 2014, even 10 years after that, I mean, it took about 22 years that Carly and Guillet discovered that these codes are actually good against side channel and fault attacks, in general fault attacks. I mean fault attack, I mean side channel, fault injection, and the Trojan horses, etc. So I mentioned orthogonal direct sum masking in the first hour, and how LCD and LCP also codes are good in that setup. So, one more remarkable work, I mean, I didn't mention that in the first hour. This is even more recent. They managed, I say managed, to show that taken any linear code, okay, of in the with respect to the Euclidean inner product, where the field size is bigger than 3, that means from F4 on, okay, and with respect to the Hermitian inner product from, again, we cannot get anything for F4, but after there you can find anything for the square fields. Okay, let's say starting from F9 on. I mean, that is the smallest you have after that. So, any chosen linear code is equivalent to an LCD code. That means, I mean, that result sort of generalizes Massey's result saying, I mean, LCD codes are as good as the linear codes, okay? But that is explicit. So, once you have this result, I mean, for this field, I mean, almost all the finite fields, okay? Except F2 and F3. You know this result holds. And you have this result for the Hermitian LCD codes, except F4, except the ones over F4. So, no other explicit constructions are necessary now. Okay? Now the challenge is to find good LCD codes over, I mean, binary and ternary with respect to the Euclidean, and also Hermitian ones only F4. Because above that, I mean, above those sizes, we know that they are, I mean, I can simply work with an arbitrary linear code. It is usually, not always, but usually, very challenging to compete with random codes, okay? I mean, people won't want to learn about your complicated constructions, okay? They will simply work with the random code that they can get off. In the engineering applications is what I'm talking about. I mean, they will never wonder how beautiful your curves look, how beautiful results you get from commutative algebra. They will just pick the first random code because they can. Here is the result. I mean, they can. Because they perform as good. I mean, you know that there is an equivalent LCD code for any randomly chosen code. So they will continue with that. Constructions still matter in the, again I am saying binary, ternary, and there is a high competition, by the way. I mean, especially Japanese groups are searching so hard, finding counterexamples, etc. And it is conjectured that it is not true for binary, at least. I mean, not any chosen code is equivalent to an LCD. And many counterexamples are now raining from many contributors. But no specific class is determined not being LCD, for instance. I mean, nobody introduced so far, I mean, as a published paper, that this class is generated that way using this method is never going to be LCD. There is no such result. Okay, there are particular results, but no generic results. Also for the ternary, I mean, there are a few codes that are known to be not LCD, never going to be equivalent to LCD, but I mean, no one can prove a generic result. Sufficient necessary conditions missing. Okay, this has become now the challenge. Also for the Hermitian case, I mean, with respect to the Hermitian product. So whatever you are going to do, I mean, if you are interested in that LCD, LCP business, I mean, what really matters is left a ternary, binary, and F4 for the Hermitian setup. I mean, their constructions still matter. So before this happened, I mean, we had a few works, again, using algebraic constructions, and those are what I'm going to tell you about today. Namely, let's go to there. This is the first work. Okay, quasi-cyclic LCDs. Another one, generalized quasi-cyclic. Part of this work is devoted to LCDs. I will only mention that part. And Cem Güner is my PhD advisor, by the way. And these two, well, they look like they are two separate works published in two separate papers, but I always tend to consider them as a unique paper because they are so closely related. But here, Khatun is a PhD student in Saudi Arabia, and she needed two submitted papers to graduate. That's why it is split into two. So sometimes conditions determine the number of publications. So I will slightly mention the self-dual case. I mean, if the time allows. It is so closely related. I mean, once you have an explicit construction, it is usually easy to determine the other end as well. I mean, self-dual is a bit in contrast with being LCD, right? I mean, C is equal to C dual. On the other hand, you are completely disconnected from the deal. I mean, they are like contrasting concepts of each other. But in algebraic terms, they can be characterized in a very analogous way. Okay? So I will try to mention the highlights of that work as well. Here, the basic motivations are to study the algebraic structure in terms of the symmetries that those codes have. So, I mean, after cyclic codes, this is the first class that you can think of, okay? I mean, once the cyclic case is settled. Enumeration and asymptotics are the other concerns to be settled. So, after introducing those code classes in concern, I mean quasi-cyclic, and for those last two, a special quasi-twisted code is in consideration, namely negacirculant ones, and then generalized quasi-cyclic ones. So those are really closely related. After describing their algebraic structure, I will try to show you how the asymptotic studies are done in three different ways. Okay? So that you have a generic notion about the, a generic idea about the notions of algebraic coding theory. That is actually the purpose. So let me start with the general definition of quasi-twisted. So those are one step more general than the quasi-cyclic. Instead of the usual cyclic shift, we consider constant shifts, determined by a non-zero element of the base field, let's say alpha. So you shift the vector of length n by one position again, but you multiply with alpha, that shifted position. So, and the quasi-twisted code is invariant under alpha constant shift L times, okay? We say alpha is the shifting parameter, okay? Alpha is the shifting parameter, L is the index, and N is the co-index, okay? And the code length is N times L. We have, let's say, alpha quasi-twisted code of length NL, of index L, and co-index N, okay? Those codes are slightly interesting because, I mean, co-index N will determine the algebraic properties, the so-called cyclicity, okay? This cyclic-like properties will come from the co-index. On the other hand, they are a bit linear too. So that will be determined by the index. I mean, such codes have both, I mean, algebraic properties and the random linear properties altogether, ending up very good parameters in general. I mean, all those codes, quasi-cyclic, quasi-twisted, are shown to be asymptotically good. I mean, in terms of the distance, they're really good, whereas this problem is widely open since decades for cyclic. It is not known. No one could show if cyclic codes are good or bad. So it's a very, very challenging problem, by the way. I mean, and so for those people we know, I mean, they have good families of code. So that makes them interesting. I mean, once you add a bit linearity to that cyclicity, it ends up very good in terms of distance. I continue. Okay, of course, I mean, if you take alpha equals 1, or if you are over the binary field, I mean, you are talking about quasi-cyclic, in fact. So, what else? We have to invoke a linear and the polynomial representation for those. So instead of row vector, we adopt a column vector for the L equals 1 case, okay? And this way, we will be able to generalize to quasi-twisted setup, but for once, for L equals 1, let's recall the polynomial representation of a constant cyclic code, which lives as an ideal in that quotient ring, R. So, constant cyclic codes can be viewed as ideals in that quotient ring R because they are closed under multiplication by X once they are represented as polynomials. And the map is simple. I mean, you map all those entries, all those bits as coefficients of this polynomial, and this quotient ring is nothing but all the polynomials up to the degree n minus 1. So, you will be always living there as an ideal once you have a constant cyclic code, and that's it. And that notion generalizes to quasi-twisted as follows. Now you have L column vectors, okay? Instead of 1, you have L. And all of them, again, invariant under constant shift, okay? So you have row shift invariance in that case. That just allows us to see stuff a bit clearer, okay? So alpha shift invariance, alpha constant shift at each positions in the lowest row ends up in the quasi-twisted setup. So we say row constant shift is the, okay, L positions, it can go to the top, okay? Once you map all the columns to a polynomial in R, you get an L tuple in R to the L, okay? And all of them, all those polynomials, L polynomials, are again invariant under multiplication by X, okay? Once you multiply by X, what happens in the polynomial? The last one, x to the m minus 1 becomes x to the n. So modulo x to the m minus 1, it becomes 1. Hop, it becomes the, it comes to the top as the constant coefficient. And you shift all the bits by 1. It is easy to check by hand. So, again, coordinate-wise multiplication by x makes a quasi-twisted code an R module in R to the L. So, vector spaces over rings are modules. They're not, vector space is a field correspondent of that, okay? So we can view any given quasi-twisted code as an R submodule in R to the L, okay? polynomial representations are handy in any case, okay? In that case, I mean, it is both keeping the constant cyclic structure where each component of L, I mean, up from C0 up to CL, all of them are like, I mean, constant cyclic codes glued next to each other. But also, since they are multiple, it gives you the notion of a linear code over the quotient ring R, okay? So, this is how it is. One significant difference with quasi-cyclic is that, I mean, of course, I mean, in order to characterize LCD, we will need the notion of the dual of the code. I mean, it is essential for being LCD. If the code is defined over this type of quotient ring, then the dual is living there. I mean, it is not the same ring. It is someone else, isomorphic but different. Okay? Because if the code itself is closed after alpha constant shift, then the dual must be 1 over alpha shift invariant. Okay? This is your shift parameter. Then this is the point where the ring duality and the scalar duality differs from each other. I mean, scalar-wise, okay, both codes are over FQ, and I mean, the scalar linear duality is one thing, but ring duality is something else. They are not over the same ring. So that will cause technical casualties, and that's why we will be interested in alpha equals plus or minus only. So that 1 over alpha is equal to alpha. So that makes things easier. For the computation of also self-duality, both LCD. We want them to be over the same ring. I mean, we just simply want them, yeah. We simply want to consider this case. Okay? For the rest, of course, there are works. I mean, you might want to check Esmaili and Yari, where they provide some constructions where alpha is different from plus or minus 1. But for now, I mean, for today, whatever I am going to talk about, we'll consider that case. A few more setup for the alpha equals minus 1 game. Well, I mean, once we have plus 1, you must see, I mean, it is a quasi-cyclic. For minus 1, we have some special names, so to say. Negacirculant. So, negacycle is corresponding to the case by alpha is equal to minus 1, okay? Once you shift everything and multiply by minus 1, this is called negashift. So negacirculant codes will be determined by that special type of shift. And the double circulant code, it is very similar to double circulants. It will have a systematic generator matrices A, and identity, and include with some negacirculant matrix, square matrix, okay? So, by negacirculant, of course, we need, I mean, you construct the circulant matrix by constructing the remaining rows by successive negashifts. And you can extend this notion to arbitrary number of indices, okay? You can construct 3 negacirculant, and multi-negacirculant is just the most general version of it. You are just giving this name for that particular constant shift, okay? It is just a special case. So that means, first of all, we are considering one generator codes, okay? That means one generator. We don't have the number of generators are determined by the number of circulants, okay? If you have one block, it is one generator. If you have a second block at the bottom, then you have 2 generators, etc., okay? In terms of polynomials, all these will be characterized, of course, in terms of polynomials. With identity, we associate 1. I mean, it is the natural thing. With the first row of this negacirculant matrix, we will determine a matrix, and the remaining rows will be characterized by x times that polynomial, and then x squared, up to x to the n minus 1, okay? Each successive negashifts. So, this is a particular quasi-twisted code where your shift parameter is alpha is equal to minus 1, again, I mean, depending on the index, you have n times L and one generator code. Yeah, this is what I said in short. One more generalization, I guess, coming. Yeah, GQCs, generalized quasi-cyclics, where you relax the condition on the block lengths. So in quasi-cyclic, quasi-twisted, all the blocks of have the same length, okay, m, so that you can put everything in a nice matrix form, okay, all the m rows of length L in a compact form. This is a relaxation of that condition. So instead of working with one quotient ring R only, you take L of them, L different of them, not necessarily the same. And you consider this product of quotient rings, okay? Then it becomes generalized quasi-cyclic, where, I mean, the code is living there as a submodule again, but as I said, I mean, with different lengths, nj's, okay? Each block of length nj is again invariant under cyclic shift, but not necessarily the same. It corresponds to quasi-cyclic, where all the co-indices are equal to each other. Okay? So that is one generalization. Okay. So this is, I guess, this CRT decomposition of quasi-cyclic cause. I think it is studied in 2001, I guess, by Linkson and Patrick. And it has been one seminal work for the algebraic coding theorists who are interested in quasi-cyclic and its generalizations. I mean, it is so seminal, how to say, I mean, maybe 4-digit numbers of citations, I guess. I mean, everybody is studying that, this class of course, more or less using that structure. So it starts with the prime decomposition of the polynomial x to the n plus or minus 1. Since we have now, I mean, we are considering, of course, the polynomials x to the n minus alpha. Let's recall that. I mean, alpha is plus or minus 1, so we are considering x to the n plus or minus 1. Both of those polynomials are self-reciprocal. So its irreducible factorization should consist of either self-reciprocal polynomials or reciprocal pairs. I mean, anybody coming should bring its reciprocal with, either itself or someone else. That should be in that packing form. So we adopt this notation. We call GJs are the self-reciprocal factors, and that star denotes the reciprocation. I mean, we say S self-reciprocal factors and T reciprocal pairs. So Chinese remainder theorem tells us that the quotient ring R decomposes into this direct sum. I think Jitman also mentioned, I mean, this decomposition in a slightly different setup and in a more general way, because here we usually assume that n is relatively prime to q. He didn't use, in his talk, he didn't use the, that assumption that n is relatively prime to q, but here we usually assume that. So, if you have a close look at each of these direct summands, each of them modulo some irreducible polynomial. I mean, the polynomial ring modulo some irreducible polynomial. This is how you construct finite fields, okay? Each of them are isomorphic of a finite field extension of fq of degree of that irreducible factor. So this is an extension of degree of gi, okay? And all these are actually isomorphic to field extensions, just because those factors are irreducible, okay? So let's adopt some notation for them as well. Oops. Yeah. Let's take either a primitive nth or two nth root of unity, depending on if you are working with x to the n plus 1 or minus 1, okay? If you are with plus 1, then you need nth root of minus 1, which happens to be 2 nth root of 1. So if you are working with x to the n minus 1, you need nth root of unity, okay? So that psi to the n is plus or minus 1, and you have this holding, and let's choose some roots, okay? For each factor. So that isomorphic finite field extensions are constructed by joining those roots to the finite field FQ. Okay? I mean, you just construct the extensions that way, as many of you know. Now I can rewrite that equivalence that way. I mean, instead of polynomial ring quotients, I can rewrite everything in that form. I just joined the roots of each factor to the finite field FQ. Again, that plus or minus is determined by x to the n plus or minus 1. So, once you have this, you can give names to those extensions. Let's say GIs, HJs, and the HJ double prime, HJ prime, HJ double prime for each of those extensions over here. And the quasi-twisted code, or the quasi-cyclic code, decomposes into linear codes of length L over those extensions. So conceptually, it is hard to digest. I know. I mean, I don't expect you to get it right away, but think in that form. So this can be observed the easiest by using discrete Fourier transform. Okay, let's say you have all the nth roots of unity. Okay, and you have the polynomial description of the code. What you have to do is that to choose one root of each polynomial, I mean that is in the decomposition, here GIs, HJs, and evaluate those polynomials at each of those roots. This is how you get the constituents. What you obtain is, I mean, once you evaluate the polynomials, you get scalars, right? So you obtain linear codes of length L over some extensions, over whatever polynomial that you are using. That is determined. The extension degree is determined by the irreducible factor you are using, and also whatever nth root of unity you are using is also determined by the very same polynomial. So once you do the evaluations, you can get the constituents. What are the advantages of such a construction is that, first of all, those are shorter codes, okay? So if you are going to make a search, that makes more sense. Okay, that is faster. I mean, looking for a code n times L is far more costly than looking for codes of length L. Even independent of the field size, I mean, working with shorter codes is easier. And also, it will allow us to characterize anything regarding the dual as well, because the dual has a similar structure too. Hence, I mean, characterizing self-duality, LCDness, or whatever you want to, self-orthogonality, and anything that you want to do with the hull of the code is easier with that. Okay? Once you get the idea how to use Chinese remainder theorem decomposition of ideals in that setup, everything else is easier. And luckily, I mean, for each code class that I mentioned, I mean, quasi-twisted, quasi-cyclic, generalized quasi-cyclic, they all adopt this that type of structure. So it will be a unified characterization for all of them. Let me continue with one example, how things work for the double circlant or double negacirclant. So let's say you have your code over this quotient. I always mix them up. I mean, it will make me dizzy in the end. So over this quotient ring, let's say, okay? It is double circlant or double negacirclant, let's recall, that means index 2, okay? Index 2 codes. So they are generated by two polynomials. One is the constant polynomial 1, representing the identity part of the scalar matrix, and AX, representing the circlant or negacirclant part of the matrix on the right-hand side. So these are the corresponding polynomial generators. And as I said, it is always one generator with respect to the polynomials. So what you only have to do is that to evaluate, as I said, evaluate at the corresponding root. For each of them, for each CI, which corresponds to self-reciprocal factors, you have to evaluate, you just have to choose one root of each GI, let's say psi to the UI, and evaluate there. So you get your constituent. For the rest, you just choose again roots, but we know how they are related. I mean, for the reciprocal pairs, right? If A is a root of some polynomial H, then, I mean, A to the minus 1 is the root of the reciprocal of it. So it is easy to characterize. I mean, choosing for one is enough. We know how to characterize the rest. So this gives the picture of discrete Fourier transform, actually. For the inverse transform, it is far more complicated. I am not going to mention that. It is characterized by some trace maps. What you do is, again, I mean, packing everyone under some trace map, but I mean, in case you are interested, link Soleil paper 2001. So, the dual, as I said, I mean, this is what I need for my purposes. Not the trace map, but this is exactly what we need. The characterization of the dual in terms of the component codes again. And then the rest is easy. Then the rest is building a relation component-wise. Okay? So C was the direct sum of Ci's plus Cj primes and the Cj double primes. Component-wise, we have to compare. Okay? So if you want to make the intersection with the dual trivial, then you have to do it component-wise. Okay? Let me just, I mean, before going to the characterization, I just want to show you one example about GQCs. I don't want to explain you how the CRT works there, but I just want to explain you how things work in the generalized quasi-cyclic. Maybe it will help you to understand, I mean, how things work in the other cases as well, because the notation in the generalized quasi-cyclic is very ugly. I'm telling you, it is super ugly. I mean, so many indexes, so many letters are wasted. I mean, at some point, we were done with the Latin and Greek alphabet. I mean, I remember that. So, generalized quasi-cyclic example is chosen binary here. And we choose two co-indices. Remember that, I mean, we have different block lengths. So, we choose 1, 2, 3, 3, 5, and 9, and the index is 3. Okay? We are in the binary case, so what do we have? The product of those three quotient rings, where they decompose into irreducible factors that way. Let me just tell you that, I mean, this is chosen on purpose. There are no reciprocal pairs. Okay? All those factors are self-reciprocal. For the ease, okay, for now. So, the CRT decomposition of generalized quasi-cyclic is studied actually by Esmaili and Yari first. And their idea is really nice. I mean, what they do is that instead of creating sub-decompositions, let's put all the irreducible factors in a bag, okay? And let's enumerate them in a way that, I mean, the total number of irreducible factors are considered. And once any of those, I mean, x to the nj minus 1s are required, I mean, with that particular factor, then we can assign it there. How does it run? That way. I mean, the total number of irreducible factors is, let's say, x plus 1 is 1, x squared plus x plus 1 is 2, which is shared by only 2, whereas x plus 1 is on every one. And this is the third one, this is the fourth one, okay? We just give numbers, and all the factors are that much over all the three decompositions, okay? So now we will distribute. So, the extension fields that are required are here, up onto the degrees. I mean, it is easy to guess. I need F2, F4, F16, and F64. Those are all the extensions I need, given the degrees of the irreducible factors. And here is how we construct the them per factorization. So, for the first one, second one, third one, and the fourth one. Here, what do we have? This one corresponds to E1 is equal to F1, so that is characterized by x plus 1, which is common in all of them. Okay? For the second one, we have it on the first one and the third one, and the second one is set to 0. For this one, it appears only on the second one, I mean only on the second factorization, x to the 5 minus 1, so it is only there, elsewhere it is 0. That means there is no extension there, no correspondent. So the similar way you do for the fourth one. So this is a CRT decomposition with holes. That is what is happening in the generalized quasi-cyclic case. In the quasi-cyclic or quasi-twisted, you have everybody full, no zeros, and the same extension field. Everybody full, okay? No zeros at all. On this one we have. And how things run, I mean, once you adapt this notation, then you can mimic the previous setup by adopting this notation with holes again. You have 1, 2, 3, 4, 5 holes in total, but still the notation works. And then everything runs in a similar way, where the evaluations, I mean, in the end, I mean, in order to generate the constituents, as I said, I mean, you have to choose roots and then evaluate. That's it. The evaluation has some gaps as well. I mean, some holes of zeros. But that is the only difference. Except that, I mean, whatever I have shown you before, the CRT decomposition and everything, you can keep the notation. Everything works for them as well. So from now on, I mean, any characterization that I'm going to talk about holds for all of them. Once you unify the notation that way, it works for all of them. Okay, so far so good. Are you still able to follow? Huh? I mean it. I mean, at the beginning, it was very hard for me as well. But it is not only about understanding everything. It is about developing a culture. For example, in order to learn a language, the best way they say is that, I mean, open the TV in that language and listen. Doesn't matter how, I mean, less your knowledge are. In the end, the ear is recording to your brain. So this is more about that. I mean, even though you don't understand or you are not interested, I mean, you never know. You can see at some point of your research, you can see something that you might think, this can be related, I mean, to something. In any lectures, let's say, I mean, you saw something and somebody mentioned some concept about the quantum stabilizers. You can think of, Dr. Ezeman told us about something like that. Let's write him. I mean, if anyone who knows about that connection is that person, let's write it. I mean, this is also about knowing the, how to say, interests of various people. I mean, this has been very lucky, this school, in that sense. I mean, you know who is now interested in what type of research and who you can consult, and please don't be shy. I mean, none of us are native speakers, first of all. I mean, please don't be shy with your English. I mean, my English is not perfect at all. So, second, don't be shy with your research as well. I mean, this is how you build connections, okay? I know it is harder. I was very shy at the beginning, so I know it is hopeless to say that. Every generation will come and say here, don't be shy, and I was shy. So, I mean, for me, having the courage to step up giving a lecture, it was very hard actually. I was very, very shy. So, but you have to force. Really, you have to force. So, for the ones who can still follow, I mean, you can simply download the relevant papers from my ResearchGate page very easily. I mean, if you want to read it, to see how this old notation works, etc. But I will just go over very quickly over that characterization. So let's say we have a quasi-twisted code or a generalized quasi-cyclic code or a quasi-cyclic code with that decomposition. So being LCD is characterized very easily, again component-wise. I mean, once you have the code, you have the dual decomposition. Easy. You do it component-wise and get, I mean, for the CIs, they have to be unrelated with their Hermitian duals. Okay, because over the square fields, over the self-reciprocal factors, we adopt the Hermitian inner product. And over those, Euclidean inner product is running. So, I mean, I am just going fast, by the way. I mean, assuming that I don't want to repeat everything that Dr. Jetman said. I mean, I don't want to overlap with that too many times. All you need to remember is that once you have that decomposition, you compare everybody component-wise, okay? And being LCD is also very similar. You just have to be careful with your index. Because, I mean, first of all, you require an even length. And then -1 must be a square modulo q. I mean, I am talking about the order of -1 modulo q. So once every condition is satisfied, that you can characterize being self-dual in a very, very similar way. I mean, instead of making them unrelated, you make them equal. Okay? Here, they become, okay, the trivial intersection becomes here equality. You really compare them component-wise. And here, again, a trivial intersection becomes equality. Just like in the big sense, I mean, either C and C dual intersect trivially, or they're equal for the self-duality. Okay? So this is what you have. Any questions so far, by the way? I feel like I have to give a... Okay. This is one thing that is actually independently done by Jensen in '85. I want to go back to the first decomposition to say something about it. This. You have two choices to consider each direct semantic. I mean, let's take this one. This can be considered as a field extension, as I said, naturally. I mean, this is how you construct field extensions. Or, this is an irreducible polynomial, okay? This can be considered as a minimal cyclic code. I don't know if you ever heard something like that. Minimal cyclic codes are the cyclic codes with irreducible check polynomials. Not generating polynomials, but check polynomials. And this is what it is. Two possibilities. Once you choose the path of viewing them as field extensions, then you go to the CRT decomposition. Once you see them as minimal cyclic codes at each path, then you go to the Jensen's concatenated structure, which are totally isomorphic. I mean, we are talking about more or less the same stuff, but in different languages. So, this is what he is saying. We assign now generating primitive idempotence for each those minimal cyclic code of length L. Generating primitive idempotent is, well, instead of working with that irreducible factor itself, we are working with an idempotent. Idempotent means E squared is equal to E. That's all. Okay? And you can always find primitive idempotent generators if you are in the semi-simple case. That means the co-index is relatively prime to Q. That's why we always require that if we are using that. Why do we need that? To study asymptotics from one sense. As I said at the beginning, I will try to provide you 3 different proofs for 3 different code classes to show them they are asymptotically good. Okay? This is one tool that we will require. Remember that the CRT decomposition was isomorphism, okay? This is isomorphism, not equality, because you have the direct sum of codes of length L in the end, and the number is ST, I mean, you don't have a control, and this code, I mean, or quasi-twisted code is of length N times L, okay? They are not necessarily equal, but this is an isomorphism anyway. The exact equality is given by this. You see, this is exact equality. So, if you have shorter linear codes of length L over various extensions, you can replace the coordinates of this by polynomials by using this structure, okay? So, this is the other way around. You have linear codes over various extensions that are determined by the Chinese remainder theorem, okay? Now forget the technicalities. So, what you want to construct is a quasi-cyclic or quasi-twisted code of length N times L. Hence, you want to replace those scalars coming from extension field by polynomials, okay? Once you do that, you obtain the polynomial representation. So this is telling you how to do this, okay? So, concatenated codes are actually, I mean, they go back to 70s by Patterson and Costello. Many people studied concatenated codes, but Jensen, who is actually the student of Eustace and who invented quasi-cyclic codes, studied this first for 2D cyclic codes and then for quasi-cyclic codes, showing, I mean, once you have shorter codes over extension fields, how you can construct quasi-cyclics, okay? What is it useful for? For the bound minimum distance bound he created. And I am very free to say that this is the best known for the codes of this family. By the family, I mean quasi-cyclic, again, generalized or not, quasi-twisted or not. It works for all of them. Anybody with a CRT decomposition, it works. And we don't know anything better than this. For cyclic, there is a zoo of bounds. Like, I mean, there is BCH bound and then generalized to HT bound, and we know who is better than the other one, okay? And then it is generalized both ways, like Schiff bound, Ross bound. Both of them generalizing Hartmann-Senk bound, HT bound. So we know how things work. And then there are coming Hasse-Weil bound, coming from geometry. We know in which lengths it is performing or not. On the poor quasi-cyclic codes are without bounds, guys. I mean, there are very few bounds and all of them are super bad. Except this one, a bit remarkable than the rest of the bounds that are proposed. So basically, if you know the constituents, okay, the non-zero ones are the ones that are interesting for this bound. So we assume such an ordering of minimum distances over the non-zero constituents. Of course, they can be zero, I mean. But they are not interesting if you want to derive a minimum distance bound, of course. The minimum distance of a zero code is undefined. So we take the non-zero ones and we consider the cyclic codes that are playing a role for those linear codes, because we will use the polynomial code words to replace in the code words of this. So we assume such a minimum distance bound. So again, as I said, 3 different types of asymptotics. But first the quasi-cyclic, and then generalized quasi-cyclic, and then those multi-negacirculant via enumeration. Okay? So I will recall some concepts of asymptotics. Well, 2 important parameters are the relative rate and the relative distance. Okay? They are defined that way. I mean, you can find them over any book of coding theory. This is important, the relative rate, and this is important, and they should be different than 0 once you send the code length to infinity. Okay? In one way or the other. The question is, I mean, which one is going to be sent to infinity? Index or co-index? That is also an important question. We are going to keep the co-index as a constant, and we will send the index to infinite. Okay, that is one tricky part. And what else? Entropy function. I think this is recalled by many, many lecturers so far. So that is a known thing. And the Gilbert-Branchot bound. This is what it is. This is how the relative rate and the relative distance are related to each other. Okay? So, if you can find good families of codes satisfying this, then you can say that my code is asymptotically good. Or, an alternative way is to say, okay, for a certain family that I constructed explicitly, I can measure the rate and the relative distance, and they are not 0, so my codes are good. I mean, those are the standard techniques that you use to say your codes are good. They have good error correction capacities, which are never going to be used anymore, but still, if we want to know. Okay? So, the first one. So you have to split it into 2 cases, the self-reciprocal part and the reciprocal pairs. Okay? This is the Euclidean part, the self-reciprocal pairs. Okay? Once for the Euclidean linear product. So we put the assumption that on M and Q to be relatively prime, plus Q is never congruent to -1 over any power. Okay? Otherwise, you fall into a self-reciprocal case. So, it is one or the other. Here, the condition on M and Q guarantees that, psi and psi minus 1 have distinct minimal polynomials, H and H double prime, because, whatever power you take over Q, let's recall that given an irreducible polynomial, all the roots are the Frobenius powers of someone, right? You can fix one, the others are Q powers of that. So this condition just guarantees that, two separate reciprocal factors. Fine, let's assign names for them. Okay, H double prime, and they have to be the same. Adjoining one root and the minus 1 power is actually the same thing. We just want to assign different names for the notation, but of course they are the same extension field in the end. So we are considering only one asymptotically good sequence of LCD codes, and they exist, either by Massey or by Sandria. That's why I showed you at the beginning. They both showed in different ways that LCD codes are good. Linear LCD codes are good. So, since they are good, I know I can take a family of good sequence of LCD codes. And then I concatenate them with the corresponding minimal cyclic codes. That means I have, for each member of that sequence, I can replace the coordinates by polynomials to construct a quasi-twisted or quasi-cyclic, in this case quasi-cyclic code. Okay? You can do that for quasi-twisted as well. What you have to do is to replace it with minimal constant cyclic codes. It's the same thing, same story. You just have to be careful with the duality. So, once you have done that, you can use Jensen's bound to do the comparison. Namely, he says, by using the Jensen's bound, you can simply say that the constructed sequence of quasi-cyclic LCD codes have this minimum distance at least. And then rate is also easy to construct because you have only two direct summands, okay? Over two direct summands, it is sort of easier to compute everything, okay? And this is known to be finite, because each CI was good. So, by being good, this is non-zero. And this is a non-zero constant, 2E over M. E is the extension degree, okay? And this is also non-zero, because this is non-zero. Distance is not zero, M is not zero, of course. And DI over LI is assumed to be non-zero, because I assume CIs are good. Okay, that comes from the definition of goodness. Anyway, by just taking random linear codes, you can construct good sequences of quasi-cyclic codes that way, with respect to the Euclidean inner product. For the Hermitian one, you need the Hermitianized version of Massey's identity. Okay? That was missing, but it is easy to fill that gap. This is the Hermitian version of it. Instead of GG transpose, you have GG conjugate transpose for the Hermitian inner product. It's the same. So, the proof is easy, by the way. It is really, really, really easy. What really matters is that the Massey's identity for the arbitrary linear codes. So, here, if you have a linear code of, length L, because we are interested in that length, with some generator matrix of that form, in the standard form, here is P is the redundant part, then using this, you can construct an Hermitian LCD code with those parameters, and the distance satisfies this. With that, you can simply say, Hermitian LCD codes are as good as the linear codes that they are associated with, just because of that property. And the construction is almost identical to Massey's theorem. That's why I told you that I will come back to that. He uses this. Okay? If the characteristic is 2, his construction still works. That was his trick, to construct such parameters. Okay? Instead of that, if the characteristic is bigger than 2, this is the modified version of it. We just multiply it by some A, where A is an S plus 1th root of -1. So, once you have those two different options, you construct a code of length, I mean, here k is here, k plus, here it is L minus k, okay? 2 times L minus k plus k, and the dimension is the same. Because, I mean, identity really determines the dimension, by the way, it is of dimension k. So, this is almost the same proof as Massey, but in the Hermitian setup. We need that for the self-reciprocal factor part, and after that we are done. And this is the contrasting part of it. I mean, we have assumed, again, I mean, M and Q are relatively prime, fine, but now Q has a power that is equivalent to -1 modulo Q, mod M, sorry. Then we can construct a good sequence of LCD codes with respect to the Hermitian inner product, okay? So, this condition actually guarantees that psi and psi minus 1 have the same reciprocal minimum, self-reciprocal minimal polynomial. That is the condition. And any, I mean, irreducible factor should fit one case or the other. So, again, the same thing. We take a good sequence of Hermitian LCD codes now. Now we have shown, I mean, they exist. That there exist asymptotically good Hermitian LCD codes. Now let's take one sequence and concatenate them with the corresponding minimal cyclic codes and construct a sequence of quasi-cyclic codes that are LCD, and the rest is to show them that they are good. That's all. And the same way, I mean, you can use again Jensen's bound to show that they are as good as CIs, because I mean, because of the goodness. Again, you have to set the same limits and show that, okay, I am just multiplying it by a positive constant, so this was non-zero, the result is non-zero. I mean, and all the arguments that are coming with. Of course, I mean, those take pages to write down. I am just giving you the highlights. And the reason I am writing down them here is if you want to go back and read, I mean, you can have a brief idea before starting reading the paper. I mean, the slides are usually prepared that way. So, not because that you have to read and follow everything, okay? I mean, I am getting that you are digesting your lunch and you are getting sleepier. Once I go deeper into technical stuff, it's okay. I mean, my purpose to put all those details is that, I mean, for the readers, don't worry, okay? So, that is one method that you can use. I mean, the limit definition of being asymptotically good. That is one way, okay? For GQC, it is a rather funnier trick. I will come back to that, by the way. I want to show you the LCD first. The slides are not, how to say, organized in the way I wanted, because I wasn't informed that we have to start early in the morning. I was running in the morning with the slides on the USB stick in the mornings, so that, I mean, I couldn't put them in the order that I wanted to, so I will be jumping over and over, sorry about that. So this is a trick that you use. Now we have shown that quasi-cyclic LCDs are good. Okay, that is one thing in the pocket. So now I want to use that fact to show that GQCs are good. And the trick we use is to use the so-called UE construction. That is known as a UE construction. Or you can also say, okay, this is the direct sum. You can take a direct sum of two quasi-cyclic codes of different coindex, of different block length, okay, to create a GQC code. That is a GQC code, but tricky. And then over this direct sum, you can show that the resulting GQC code can end up being good. How come? This is the thing. So, here, this direct sum, I mean, of course, the length is clear. It is M1 plus N2. And the dimension is also determined by the dimensions of C1 and C2, and the minimum distance satisfied. Okay, those are known facts. If I take, I mean, quasi-cyclic codes, okay, that are good, by pasting them next to each other, I can construct a good sequence of GQCs. It is just, I mean, instead of taking cyclic codes of different length, we are taking quasi-cyclic codes of different co-index. Because if you start with cyclic codes, let me remind you that their asymptotic performance is unknown, but a big, big unknown. I mean, it's a big problem. Let's start with the known one then. I mean, it is like, I mean, I start with code with 5 times 2, and then 7 times 2, okay? 5 and 7 are the co-indices. By setting them next to each other, you can construct a GQC. And then you can show that a GQC code sequence that is constructed that way can be good. Well, you do some sacrifices. Here is the sacrifice you make, the minimum, but still, it's good. So as long as it works, I mean, there's no harm that you can do it that way. This is a trick, by the way. I mean, it is really, really a trick that you can use. So it really requires the asymptotic performance of the quasi-cyclic codes that are LCD. I mean, without that result, you cannot construct that. But still, it works. Okay, before going to the other type of asymptotics, I mean, this is the second type. I mean, once you know that, you can use just linear algebraic methods, I mean, sometimes, to generate them. Concatenation is very complicated. I mean, technically involved, and you really have to know a lot about the commutative algebra tools that are used. This is easier. This is just direct sum. So, just linear concatenation, the linear direct sum UV construction, so everything follows very smoothly. And the, I mean, as an exercise, you can try to show it on your own. I didn't put the proofs here. You can achieve them from the paper as well, of course, but this is a nice exercise for yourself. Now I go back to the Hermitian LCD cyclic codes. So, actually, again, Jitman mentioned the abelian case of this. I mean, the abelian codes that are not necessarily semi-simple, and they are Hermitian LCD. Okay? So this is 1D case, how to characterize cyclic codes that are Hermitian LCD is this. So, instead of self-reciprocal generating polynomials, here we have the notion of conjugate self-reciprocal. I wanted to put those here because I have one slight note for you. Those conjugate self-reciprocal polynomials have some applications in DNA codes. Okay? You might want to have a look. I mean, for your research, I mean, please be aware of as many extensions as possible. These bodies have an application there because DNA code is a special code, I mean, usually defined over F4 over Z4. And it has some special reversibility constraint. And you know, I mean, DNA is characterized by 4 proteins, right? Adenine, guanine, stazine, thymine. Yeah. So you have those 4. And you can really use Hermitian codes, I mean codes with respect to the Hermitian inner product, to characterize those as well. And those are interesting applications. So this gives a room to characterize, I mean, Hermitian LCD cyclic codes. So let me continue. The idea is simple. You just have to conjugate first or apply the reciprocization or the other way around. I mean, you can choose one way or the other. It is generically the same. And then, once you have that, the Hermitian intersection, I mean the intersection between the code and its Hermitian dual here, is characterized by this, I mean, Euclidean dual conjugated. Okay? But of course, I mean, I am just giving the idea, by the way, you have to show this. And once you show this, then you have the characterization that is very similar to the Euclidean case. Okay? You have to separate the factors at all algebraic multiplicity. Do you remember that from the first part in the morning? I don't assume so, but I mean, what you are interested is to divide x to the m minus 1 plus 1, whatever it is, into 2 parts, okay? Let's say g and h. those should never have any common factor at any multiplicity. If you are considering, I mean, the non-semi-simple case, the repeated root case, everybody should stay with all the algebraic multiplicity there is. Or if the length is relatively prime to Q, well, you have to separate two factors, and either you have linear complementary pairs or LCDs, okay? In order to have LCD with respect to the Hermitian inner product requires conjugate self-reciprocal. In the Euclidean, it is just self-reciprocal, okay? That was the Yang-Massey, if you recall. Yang and Massey studied those, saying a cyclic code is LCD if and only if it is reversible, if and only if the generating polynomial is self-reciprocal. This is the Hermitian version of it. So, once you have that, you can evoke the notion of conjugate reversible, of course. I mean, mimicking Yang and Massey work. And that conjugate reversible is one notion that you can see that DNA codes papers. I mean, you might want to check. So, again, yeah, Hermitian LCD, if and only if conjugate reversible, the analogous result. You can construct 2D cyclic codes that are LCD, again, in a similar way, by taking the constituents, I mean, those component codes, to be conjugate reversible cyclic codes, or conjugate reversible constant cyclic codes, if it makes sense, okay? Wherever it makes sense. I mean plus or minus one constraint. So, once you take each CI conjugate reversible, and then again those reversible codes, then you get the LCD 2D cyclic code. That is easy to construct. And then, I mean, if you, it is, how to say, a recursive relation. If you take the constituents to be n minus 1D, then you construct an ND code with the same property. It is usually a recursive thing. I mean, in an inductive way, you can construct any dimension you want. And that paves the path to the abelian setup. Okay? I mean, you can do it in a very, very similar way. So, I have very little time left, so I don't want to make you more sleepy. So let me go to the last thing. One thing. Does it look familiar to you? The challenge. The challenge. Actually, there are 3 ways to prove it. Anything coming close to this is accepted, of course. I mean, the challenging way is the proof that is on the paper. I mean, we do not expect anyone using constituents, of course. The other one was using the concept of GG transpose, of course. I mean, that thing is GG transpose in the language of polynomials. So, if you have one AX as the polynomial generator, then the dual has one A reciprocal. Okay, that was all about it. And then, okay, one AX times one A reciprocal X would have given you this. Okay, that is the theorem here. And it is actually if and only if, not one way, but it is if and only if. So, I will skip that part, but I will show you the examples that are coming from there. So, on Magma, we tried over random polynomials AX satisfying this condition, okay? Just to have a look how short codes perform, I mean, short CD codes perform in that setup. Over double circulant and double negacirculant. And what I want to emphasize you is rather this. Here, the binary double circulant, quasi-cyclic, of course, I mean LCDs, by double circlants are quasi-cyclic. As you can see, I mean, few of them achieve the best possible distance. Okay, the ones marked with star are the ones achieving the best possible distance. D star is the best possible distance for any code of length 2n, index is 2, and dimension n. Okay? Once we try the ternary ones, ternary double negacirculant this time. So the shift parameter is -1. I get more stars. Do you recall Sandria's result that the number of LCD codes are more or less 1 minus 1 over Q, where Q is the field size. So even in short length, you can confirm it. I mean, arbitrary linear codes, of course, I mean, we know for the short length, I mean, who is the best known linear code with that code length and dimension. And over Kinary, over F5, we have a lot of stars. So they are actually dense. I mean, you can get better parameters over larger fields. Okay, that is confirmed by really easy magma search. By easy, I mean you are just looking for one polynomial. I mean, that is a really, really easy search. So these are the results confirming Sandria's result in a visual way. I mean, of course, it's not a proof, but visually you can observe that he is right. Last asymptotics, I will try to be as fast as I can. So, before that, the self-duality is very analogous. Of course, you have to set everything in that setup. The length, code length, must be even. So, you set the index to even to study that in the level of constituents as well. The constituents must be of even length because they will be required to be self-dual. So, once you have that, you have the analogous conditions for them as well, where in this case, x to the m minus 1 divides them, because GG transpose must be 0, modulo x to the m minus 1. So, that is just a characterization, and again, I mean, for double circlant, double negacirclant, the only thing that differs is a plus or minus sign, the same characterization. That's why I said, I mean, those two papers are like twins of each other. Really like mirror images. Everything characterized for self-dual can be characterized for LCD as well. So, for the performance of negacirclant codes, well, there's some number theory that are getting involved. I'm not going to give you details. There's something called Dixon Polynomials. I mean, which are special polynomials characterizing certain factorizations, let's say. Okay? And Helmut Mein have proven, I guess, for the case of Q is equivalent to 3 mod 4 case, that this special polynomial, x to the 2 to the m plus 1, factorizes into 2 irreducible factors over Fq. Okay? So the Q equals 1 mod 4 case can be found in the finite fields book of Liddell and Niederreiter. The purpose is to have 2 irreducible factors only that are reciprocals of each other, because we are going to perform an enumeration, and enumerating many constituents is a hard job. We rather have 2 of them only. You remember the S and T, the numbers that are general, that are determining the number of constituents. We want only 2. So this is how you obtain it. Over the examples, it is always easier to see the idea. If Q is 3 over ternary codes, we will always have x to the 2 to the m plus 1 decomposing into those 2 factors as long as m is bigger or equal than 2. Okay? We have only 2 factors. So, over 5, we will have those 2 factors. Okay? That is running the CRT decomposition, as you remember. So once I guarantee that I have only 2 irreducible factors, I can perform an enumeration. I will just show you the result. So a general enumeration formula is possible for short indices like 2 and 3, but for the higher ones, we really had to assume that factorization into 2 factors. So LCD double negacirclants are of that number. Index 3 of that number. Arbitrary index of that number. Okay? What we have to keep in mind is that, I mean, it is of order Q to the n L minus 1. It is of that order, because those other factors of lower power, let's say, are strictly smaller than that, and let me remind you that we are going to study the asymptotics, so things will go to infinite, so everybody will be of that order and those will be negligible. Okay? So, once we have those enumeration results, how do we study the asymptotic performance? Is always in terms of the Gilbert-Marshall bound. So, how do we do that? So, of course, there is the counterparts of the self-dual as well. I mean, the results are very, very similar, but the index must be even, so I am just showing you for index 2. I mean, the enumeration results are similar, and the assumptions are similar. That is the main part. Here, it is also assumed as a product of two irreducible polynomials. That means x minus 1 times the big polynomial, right? X to the m minus 1 plus x to the m minus 2 comes up to x plus 1. I mean, that big binomial factor. So, by using Artin's conjecture, you can set a condition on that to be irreducible. On the other case, double negacirculant case, is the same assumption. The Dixon polynomials and, well, you have two irreducible factors. So, you need one more thing. The number of codes that are containing a certain vector of a certain weight. Okay? Here is the assumption. Once you fix a vector ux in R to the L of weight strictly less than m, then there are at most that many polynomials that generate a multi-negacirculant code like this. Okay? Once you have this result, the asymptotics here, it is performed, is obtained by using this. So, the tools that you have to use. First, the volume of the Hamming ball of this distance. So, and then this is multiplied by that number so that, okay, for a certain vector, you had this result. For all the vectors in that Hamming ball, you have this total number. If you have one negacirculant code, multi-negacirculant code, in this, which is guaranteed by setting that number, showing that number that is counted, enumerated, is bigger than this, then you make sure there is at least one multi-negacirculant code inside there. Okay? Once you do that, then you show, I mean, by doing all the equations, this. Okay? Let me recall you that it was of this order. I mean, the total number of multi-negacirculant codes of the index L was of this order by the previous proposition I said. So this number must be bigger than this. So you are looking for the entropy function, this is the entropy function, HQ of lambdas, that satisfy this number being bigger than this. Once you do all the calculations, I mean, you take logarithm q, of course, and then compare the powers and do all the summation subtractions, and what you end up is this. If you solve for the HQ of delta here, this is all you need to do. This is called the method of expurgated random coding, the so-called expurgated random coding. And with that method, I think Patrick and Minja have already published, like, what, 15 papers? I am sure it is more than that, but I mean, yeah, but one class, one paper, really. I mean, one algebraic code class, one paper. It is really like that. I mean, you can check over any of those, how if you want to learn about this method, I mean, how enumeration is imported in terms of asymptotics, and how it is applied, and how you derive modified versions of Gilbert-Marshall bound. One final note, the random coding argument would say, I mean, that this HQ of delta would be bigger or equal than L minus 1 over L. Okay? So you are just half less than this Gilbert-Marshall bound. This is a modified version, which is half less than this, but still you are good. I mean, as long as you are not going to 0, you are good. This is just half of it, and you are good. Okay? Any questions? Okay, then we should release you from the school. Thanks for your attendance. Thank you.
Thank you, Dr. Buket Ozkaya, for the presentation in the last session of the summer course on coding theory and cryptography. Please stay on the stage. We will give you a souvenir as a speaker today. May I invite Dr. Indah Emilia Wijayanti to come to the stage and hand over the souvenir to the speaker.